Good morning, good afternoon, or good evening. We are still doing the 2024 Step 2 paper, and we are now looking at question 6, still within the pure section of the paper. This question is talking about what appears to be a binomial expansion style question. Scanning through, we can see part II, we're expanding out a particular series. And even in part I, we have the binomial coefficients or the Pascal coefficients in the answer there. So, diving straight in, we have a sequence Tn, which has an initial term of 1, and then a recurrence definition telling us how to link each term to the next. Prove by induction. Induction is particularly nice. I like induction a lot, particularly anytime you index anything by whole numbers, anytime you have a discrete sequence of things happening. So we can jump into this straight away. Proof by induction is very much the same every time. First, we need to check the base case. And here we just need to be a tad careful. The base case starts at 0. So the base case t of 0 is given to us by 1. And if we look at the relationship they've got, we've got 1 over 2 to the 2n. And then, so I am subbing in 0. Not subbing in 1 straight away. I fell into the trap of the base case being 1. So we have 1 over 2 to the power of 0. It's just 1 over 1. And the note given to us as 0, choose 0 is just 1 equals 1 as required. So the base case is sorted. So now we move on to the inductive case. This is the crux of a proof by induction. And the basic idea, let's assume a particular point is true. So assume tk, the pen's not playing ball, is 1 over 2 to the 2k. And then 2k choose k. Now, the difficulty is going to be if we're going to link these together, then really that binomial coefficient needs to be expanded out. So I'm actually going to do that here so that when I see it later on, I'm not going to be surprised. The binomial coefficient is the top 1 factorial over the bottom 1 factorial, and then the difference between the top and bottom factorial. So actually 2k choose k is 2k factorial over k factorial squared. So then what we really care about is the next term. And again, I've put my labels in awkwardly. So we're assuming tk, and then we're going to try and work out tk plus 1. And here we can't use the result. We can't say this is 1 over 2 to the 2k plus 1. We need to use the recurrence relation. So this is then 2 lots of k plus 1 minus 1 over 2 lots of k plus 1 of tk. Okay. So expanding, simplifying, trying to deal with this a little bit. The numerator, it simplifies as so. The denominator. Now I think I'm going to leave the denominator factorized because I know I'm going to have to find some extra 2's to put in with here. So I don't really want to expand out that 2 when I know it has to go elsewhere. Multiplied by 1 over 2 to the k, 2 to the k factorial, k factorial, k factorial. Okay, well, knowing what I'm aiming for, really want to increment this thing by 2 stages. I want to put in a 2k plus 1 and a 2k plus 2. So let's try and make that happen. So my numerator, I've got 2 to the k factorial. I already have a 2k plus 1, but I want a 2k plus 2. So I'm going to put that in the numerator straight away. In the denominator, I already had 2 to the k plus 1. I had a 2 to the 2k, and a k factorial. And because I've put that in the numerator, I need to put it in the denominator as well. And this is where the kind of the magic happens. The numerator, I have the 2k factorial and I have the next 2 terms. So I have 2 to the 2k plus 2 factorial. The denominator, I have a extra 2 here and an extra 2 that I can factor out of these. So I've got 2 extra 2's, 2 to the k plus 2. But then I've got a k plus 1, which I can shove with one of the k factorials, and another k plus 1, which I can shove with the other factorial. And therefore, ripping this back apart, the first section we can have as 2 to the 2k plus 1. And all the factorial nonsense is exactly 2 to the k, 2k plus 2, choose k plus 1, which is exactly what the formula was predicting, as required. Thus, by mathematical induction, the base case is true. It's true. And tk equals the stuff implies that tk plus 1 equals the stuff. The worst part of induction is the conclusion. Thus, by mathematical induction, the base case is true and the k implies the k plus 1. So Tn equals the stuff for all n in, I'm going to call it Z0. I should not call it Z0. I should call it N0. So these are all the natural numbers, and the little 0 says we're starting at 0. And hey, part I done. Just to check that we know what induction does. Part 2. Be intriguing to see how we use part I in the rest of the question. Part 2. Show in the binomial series for that the successive coefficients are related by. Well, that coefficient relationship is exactly what part I was talking about. And then we can see that the last part of part 2 hence prove that is exactly that recognition that AR is equal to TR for all R. Okay, well, the only sensible thing is to try and expand this and see if we can spot such a relationship. So this is going to be 1 plus n, the x thing, plus the power minus 1 over 2, the x thing squared, etc. And what we probably care more about is the general term. So the general term, and this is going to be quite awkward, because we've got these weird powers. These weird things here. Now, some things that you can note that will be helpful to notice is the negative signs. We're getting an extra negative sign in each bracket, matching exactly with an extra negative sign with each of these. So all the negative signs, at least, are going to be disappearing quite comfortably. So let's write out what we've got. We've got a negative a half, negative 3 over 2, all the way to negative a half minus n. We need to be a little bit careful with our powers here, and maybe I should call this r. And I'm not actually going to close that bracket yet because I need to think carefully about how that r is related to the power over here. So we can see that when r was 2 for this term here, we actually only subtracted 1 from the negative a half. So it's probably a lot smarter to write this as a half minus r. And if we do check with the couple of terms that we've got above, here we've got a power of 1, and we only had a half minus 1. Here, when we've got a power of 2, we do have a half minus 2, giving that negative 3 over 2. So everything does line up correctly. Over, and now the power here matches the factorial thing on the bottom over r factorial. Okay, and of course that goes on forever. The question is wanting us to link consecutive coefficients together. So I think I'm actually going to pull those coefficients out. So the AR, and I'm still a little bit concerned on when I want to start simplifying and dealing with the negative signs and other clever tricks. And I think I want to do that here. So AR, and again, notice that there are R brackets here to match with the R negative signs with the power of X. So this really is 1 times 3 times 5. Come on, pen, I believe in you. All the way up to 2r minus 1. So I've swapped all the signs, and I've pulled out a 2, a half from every single bracket. So I pulled out a 2 to the power of r, because I've got an r out of every bracket. Okay. Well, 4, and this is 4, r equals 1 all the way up. And now, no, that does start at 0. I was going to say I didn't really want to think about it starting at 0. But if I look at the relationship I'm trying to create, I do need an A0. And if we do check r is 0, it doesn't really work. And A0 equals 1. The reason it doesn't really work is if I put r is 0 into here, then I'm stopping my product at -1, but I didn't even start it at that point. So I've got some contradicting definitions floating in there just a little bit. But now let's go for 4. And we probably need to split this off. For r equals 1, 2 lots of 1 minus 1 over 2 times 1. I'm proving the result in 2 different cases, 1 minus 1. So that gives me a half, and that indeed is equal to A1. I wanted to split that one off because I split off the definition here as well. And then for r greater than 1, 2r minus 1 over 2r of AR minus 1. So now I can use that definition of AR more comfortably. It's 2R minus 1 over 2R times 1 times 3 all the way. Now, this is R minus 1, so I'm putting R minus 1 in here. So that's 2R minus 3 over 2 to the R minus 1 factorial, which gives me all of the nonsense now up to 2R minus 1. And the 2R on the denominator of this recurrence relation is exactly what's needed to boost that up, equals AR. So thus, AR equals 2R minus 1 over 2R of AR minus 1 for R equals 1, 2, and upwards. So now A0 equals T0, and their recurrence relations are the same. Their recurrence relations match. So AR equals TR for R equals 0. All the way up. It may be a bit of an excessive around the houses way of doing that. Feels like I took a lot of time to make this comment here, but it ended up working out not too badly. Okay, part 3. We now have another coefficient. BR is the coefficient of XR in this sequence. Okay, now it's told us what to think about. It's told us to think about BR over AR to find the expression involving BR for all the things. I'm actually going to turn the page because I have reached the bottom here. So let's first see what this expansion is going to be looking like. And I think I might skip straight to the general term rather than doing the first couple terms. So my general term is negative 3 over 2, negative 5 over 2, etc. Again, I'm going to leave that bracket blank for a moment while I deal with thinking about the power. And I believe, just like before, we need to increment backwards by 1. So if I do take R is 1, the first power, I've got negative half minus 1, which is just giving me the bracket of negative 3 over 2 over R factorial plus dot dot dot. So BR is, and again the negative signs all match up, is going to be 3 times 5 all the way up to 2R plus 1 this time, over 2 to the R, because I've stolen all those halves, R factorial. Now the question told us to think about BR over AR. I haven't put the question number on the side, part 3. BR over AR, and this is probably where I need AR from before. So AR was 1 times 3 times 5 to 2n minus 1 over 2 to the R factorial. Let me double check that I did quote that correctly. Yep. So if I do that first one divided by the second one, the denominators are the same, so cancel perfectly. BR has an extra 2R plus 1, and AR, I mean, that's it. So there is, quite convenient, a little hidden 1 multiplied at the front here. So although there's the same number of terms on the numerator, same number of components, really BR has 1 extra. So I don't even need that fraction line. So by considering that, find the expression for BR. But we know what AR is. we know AR is equal to TR, and TR is 1 over 2 to the 2R, 2R choose R. So BR is 2R plus 1, lots of that. Let's make sure we put everything in the right places, 2R. Amazing. Part 4. Part 3 there was really quick. Part 4. Now part 4 looks really pleasing because the initial part of, the front part of part 4 is exactly this expression for BR that we've just worked out. So something real special is about to happen. By considering the product, I'm going to scroll it so we got that slightly better in the screen. By considering the product of those, prove that. Okay. Well, certainly the product of those is the part 3 that we've just worked out. So I'm gonna make it real obvious here. 1 minus x to the negative 3 over 2 is equal to 1 minus x to the negative half, 1 minus x to the negative 1. And we've just shown in the part above that the coefficients of the first one are the things that we care about. So this is the sum from r equals 0 to infinity of BR x to the r, and that's equal to r to infinity to 0. Now that one is exactly the ARs. And we're doing that times, this is why we had the comment at the top of the question, don't worry about issues of convergence, because multiplying infinite summations together is something that in general is not really allowed. Now, the other thing to notice is what this summation, this final one is, and this one's actually really nice. 1 minus x to the power of negative 1 is simply 1 plus x plus, well, it'll be minus 1 times minus 2 over 2 factorial, cancels perfectly, plus x squared plus x cubed, etc. So that is actually just the sum from 0 to infinity of just x to the r. Okay. What the question seems to be implying, and what part 3 implies, is we should be looking at the coefficient of x to the n. So the coefficients of x to the n are, well, on the left it's just bn. Now on the right, this is now going to be a lot more challenging to work out. If we want x to the n, then we can choose no x's from the first bracket and n from the second. So we can have a0 times the x to the n coefficient of the other bracket, which is just 1. Or we could have the coefficient of 1, of coefficient of x in the first bracket with the coefficient of x minus 1. Or we can have the coefficient of or all the way up. And I will comment what this is. So this is really AR x to the r multiplied by x to the n minus r from the other bracket, cycling through the r's from 0 to n. And of course we can summarize that as a summation. This is the sum from r equals 0 to n of a r. But we know what all these things are. So by part 3, bn is 2 to the n plus 1 over 2 to the 2n, 2n choose r, equals the sum, r equals 0 to n, And then the other side is really by part 2 and part 1. By part 2 and part 1, because the ARs are the TRs, and the first part of the question, if I scroll slightly up, tells us what the TNs are. That's 1 over 2 to the 2R, 2RR. And if I check very carefully what these two look like, everything works. And really up here, I should have said for n greater than or equal to 1. So this is true for n greater than or equal to 1 as required. An odd question. There was a lot of work in the first part, and now I'm less sad about doing all of this in order to justify part 2, considering part 3 then just fell through the wash in such a pleasant way. Okay. Well, hopefully that gave you the hints and the explanations on working through a problem like this one. If you do carry on working through your step questions, good luck, and hopefully more of these will be uploaded soon.